All right, quick challenge for you guys. We're doing 3.2 and 3.3 today. Let's see, it's like day 8 or day 6 of lecture. And 3.2 is on dispersion or deviation. It's always fascinating it from the instructor's point of view. Like everyone's sitting in here, only 2 people are walking in right now. But as soon as I say, like, let's start lecture, that's when the backpacks start opening. Like no one fucking knew they were going to be taking notes 2 minutes ago. It's fucking amazing. Not a big deal. We're gonna have 2 sets, set A and set B. Set A has values. Let's go with 46, 48, 50, 52, and 54. And set B has 10, 30, 50, 70, 90. Your task to start off with is find their mean. Find the mean of each set. You asked about your polo shirt? I forgot. I was wondering if you'd forgotten or they said no. No. Yeah. I can't imagine them saying no. So did anyone get the mean for set A? 50. What about set B? It's also 50, right? These have the same mean. But looking at the data, we can tell they are clearly different. If I had a nice little number line, And we had 50 in the middle. And maybe put 25 there, 0 over here, 75 there, and 100 over here. My red values are all right here. And my blue values, I got one here, I got one over here, I got one over here, I got one over here, and I got one over here. Maybe I'll make them a little asterisk so you can see the difference. They stand out a little bit better. The red ones, the red data set, set A, the data is all clustered together. It's not spread out at all. And set B is spread out a lot more. Set B's data is spread out a lot more. And I think that's the best way I've ever presented that thing. I've never done the number line with the dashes like that. I think this makes it look pretty good. So the idea of dispersion measures how much the data is spread out. How spread out the data is. The first idea we're going to look at is range. Range is highest value minus lowest value. So this is like the first measure of dispersion. What is the range of set A and set B? Well, the highest value in A is 54, and the lowest value is 46. So this equals 8. And B, the highest value is 90 minus the lowest value is 10, is 80. So we can see the range is like looking at the range, one's got a much bigger number than the other. That's a quick and easy ballpark way of looking at it. You guys remember talking about resistance and outliers and stuff? Resistance is something that if we have a very odd value, a very extreme value, it doesn't change it. Let's check this for resistance. Is range resistant? Let's change in range, let's instead A, make 54 into 154. And now when I recompute the range of A, let's call it A2, just to make it a little bit different. I have 154 minus 46 is 108. So is range resistant to outliers? No, it had a heavy impact. It was drastically impacted by outliers. So it is non-resistant. So in fact, it is one of the least resistant ones. The other method that we're going to use for, at least for now, 3.4, 3.5, we'll have another thing that we do for this dispersion idea. But the other thing we're going to do in this section is standard deviation. Standard deviation is also not resistant, but it's more resistant. It doesn't get impacted as much. So what we're going to look at now is deviation, standard deviation, or just deviation. Often abbreviated just deviation. There are two formulas. One is for population. So population deviation. Is represented by lowercase sigma. And it's a shitty fucking formula. We have the sum of xi minus mu squared divided by capital N, and then we hit that motherfucker with a square root. Xi is the individual data points. Mu is population mean. We talked about that on Monday. And N is population size. Sample deviation, standard deviation isn't much better. In fact, it's not better. Here we use an S, and it has the same setup. We're doing the sum, we're doing xi, we're subtracting the mean. The mean for a sample is x bar. We square it. That's what we add up. We do the subtraction, we square it, then we add up the squares. Then we divide not by the population size, but by the population size minus 1. And then we take the square root. N minus 1 is called the degrees of freedom. And it's abbreviated D dot F dot. You will see that in the homework and on StatCrunch, D dot F dot. It means to take the sample size and subtract 1. And these are the formulas for bell-shaped distributions. Thankfully, you've already learned the command for how to do this in StatCrunch. We go stats, summary stats, columns. You will see two of them listed though. So the two listed are the one that's just abbreviated, it'll say STD DEV, which is a terrible fucking abbreviation, right? If you don't see it as terrible, you're not seeing it. This is for samples. And then they'll say UNADG, ADJ, STD, DEV. And if you still don't see it, you're not even hearing it either. This is for populations. What? UNAADJ. It stands for unadjusted. Unadjusted. So subtracting one, adjusted on the sample, population is unadjusted. We keep it the full samples, full population size. You almost will exclusively be using this one. Always this one. In fact, they put unadjusted standard deviation way down on the list, so you don't like fucking see it first and go, let's use that. The idea here is the greater the deviation, the greater the dispersion. And I think one way of picturing it is like a pile of sand. I'm gonna go back to that fucking setup I had. I really like this. This was good. This explains shit kind of well. Every once in a while, you have a great epiphany in fucking class while you're lecturing, and you're like, hot damn, that's the shit. For the red set, we had them all really close together. And if we had a bell curve for it, it's probably going to be pretty steep. Then we had 50. We had 30. We had 10 over here. We had 70 and we had 90. Picture it like sand in a sandbox. If it's more spread out, the sand's got to come from somewhere. So it tends to mean a smaller hill. This is going to look more like this. And this is probably going to be lower. Blue will probably go down like that, maybe. Maybe I should do that. That's a little more realistic. Let me cross off the top ones. It's not that much higher than the red on the ends. It's kind of interesting on a bell curve, believe it or not, the area under every bell curve is 1. So if we like cut it into pieces and made a square out of it, it would be a 1 by 1 square, no matter which shape it is, whether it's spiky and narrow or flatter and like more like a hill. So just like sand, if the area change, if the top of the hill goes down, that sand has got to go somewhere, and it pushes to the sides. Are we having fun yet? There's another one in this category. It's called variance. Variance has got the hardest fucking formula ever to remember. It's so hard. For populations, it's sigma squared. And for samples, it's S squared. So saying it was hard was a joke. If you have the standard deviation, you have variance. And vice versa. They like get it going from one to the other is as quick as a quick thing in the fucking calculator. We'll look at doing these in a second. I do want to talk about non-bell shaped things. And does anyone need that longer before I start getting all Yankee? Yep. I don't think I have any homework for the next part for the non-bell shaped curves. If I do, I'll make a video showing how to calculate one of them. But I'm going to tell you and show you what it is, just like the formula real quick. Mostly because I love the fucking guy's name. He's got one of the coolest fucking names in the world. In fact, I think one of my next D&D characters is going to have his name. Because it just fucking sounds really great. Yeah, play D&D. Ready? For non-bell shape, like our skewed graphs, we have, and I'm going to write it first before I pronounce it. Deviation. Doesn't that just kind of like flow off your tongue? Chevy Chev. I like it. His inequality is for k deviations greater than 1. Like this only works if you have more than 1 deviation. 1 minus 1 over k squared times 100% of the area, or 100 times 100% is the percentage of data captured within k deviations. So like if I plug in k equals 1 here, I've got 1 minus 1 is 0. It's 0%. That's not true. It captures some data, so it doesn't work for less than 1%. It doesn't work for k less than 1. That's some math shit for you. Now, what does this mean by capture percentage of the data? I think this might be easier to show you the empirical rule next, which is what we use for bell curves. You guys ready for the empirical rule? This is the table you're going to want to remember. Let's see if I can make it draw a decent bell curve. Right in the center, we have our mean. So recall mu is mean and sigma is deviation. This is both for populations. We can go out, if I add 1 mean to the mu, this is mu plus 1 deviation. Yeah. And I can do that. I'm going to do this 3 times. I'm going to add 1 mean 3 times. Or not 1 mean, 1 deviation 3 times. This will be mu plus 2 sigma. And this will be mu plus 3 sigma. And then I'm going to go the other way. Minus 1 sigma. Minus 1 sigma. Minus 1 sigma. So over here I have mu minus sigma, mu minus 2 sigma, and mu minus 3 sigma. I'll wait a second, let you guys write that shit out. So like the plus 1 means going from there to there. Picture like the histogram in here. We got a bunch of columns, and this is like a curve overlaying the columns. We're going to look at this range right here. The mu is the top of the peak. And the first deviation in either direction should be 34% of the area. So if the bell curve is flatter and the data is spread out more, the deviations have to be further from the mean. This makes it so that within plus or minus 1 deviation, we have 68% of the data. 34 plus 34. And this is called the empirical rule. Then, let's change colors. Between plus 1 deviation and plus 2 deviations, going each direction, this section is 13.5%. So if I add 13.5 and 13.5 up, I get 27. And if I add 27 to the 68, I get 95. Mu plus or minus 2 deviations captures 95% of the data. Which means all the rest, the other 5%, is everything outside of it. Which means I've got 2.5% over here, half of 5%, 2.5% over here. We'll dig down a little bit more on what's in each section. But there's not a lot in there. This tends to be when we get to hypothesis testing or after the midterm. Outside of that 90%, 95% is often considered to be the outlier areas. Outlier zone. Outlier zone is not an official like stat thing. I just came up with zone right now because that's how I roll. So what are the final percentage breakdowns out here? In this region right here, we have 2.35% and 0.15%. And this is on both sides. Such that when we do 3 deviations, mu plus or minus 3 deviations is 99.7% of the data. That is a memorizable graph. I recommend actually trying to memorize it. The stuff on the bottom is pretty easy. It's just adding 1 each time, 1 deviation each time. It's remembering the percentages. But the percentages come in pairs as they go out. This 68, 95, 99.7. 68% is the first deviation, 95% is the next deviation, and then 99.7%, the third deviation. Well worth remembering, at least those 3. Yeah.
So the percentages will always be like that.
Yes. For the empirical rule.
Will always be 34%.
Yes. So if the graph is flatter, it means that it has to be spread out more to get 34% of the data. Like the deviations will be wider. I don't know, I could draw it much wider on a single piece of paper without making it look like shit. Now, the homework will either do 1 of 2 things. The homework usually says, using the empirical rule, it'll prompt you that you're using the empirical rule. later on, after chapter 7, we learn how to do the actual percentages. Yeah. Chapter 7, we use the actual percentages. So at that point, we use the empirical rule mostly as a rule of thumb. Usually when the deviations have no decimals. I am not giving myself a lot of room to write this shit. That's some amateur shit right there. Squeeze it in on a fucking corner of a piece of paper. Let me rewrite that. That just looks sloppy. In chapter 7, once we learn how to calculate the actual percentages, we tend to use the empirical rule for when sigma equals like plus or minus 1, plus or minus 2, plus or minus 3, kind of like the whole number, the integers, the whole numbers. The actual percentage isn't too far off. In every case, it's rounded to this. I think doing more, we need to show an example with this. Like just showing you the empirical rule without numbers plugged in is kind of like not as helpful. So let's look at the IQ test. The IQ test has a mean score of 100 and a standard deviation of 15. And if you want to take a gander at it, stanfordbenetest.com is where you can take a quick version, the 12-minute test, or the long version, which is a 24-minute test. They have math questions and like reading comprehension questions in there. The 12-minute one has 50 fucking questions in it. And the 24-minute has 100 questions in it. And I guarantee you, you're gonna fucking feel demoralized when you take it. I know I did, and I have above average intelligence. I've got a decent score on it. But I think I did the longer one, and out of the 100, I maybe did like 20 of the questions. Like I didn't get shit done. There were so many questions I never got to. They have to put like a fucking truck ton of fucking questions on there for like the Einsteins in the world, because the Einsteins in the world will blow through that shit in like 3 minutes. So it's kind of hard to measure like someone that's super duper duper fucking smart. Like almost unhealthily smart. They need a lot of questions. I say unhealthily smart because when I transferred to UC Merced, there was a guy studying physics and mathematics, and he is probably the smartest person I've ever met. He made me fucking feel stupid. And that's fucking hard. I usually am one of the smartest people in the room. I felt stupid when he was around. But his communication skills were, I don't want to say non-existent because that's not bad enough. They were like negative. They were negative communication skills. He couldn't fucking share what he was doing. He couldn't even talk about what he was good with other people because he would always try to go at such a fucking high level. No one could understand it. It was just, and I tried to help him for like 2 years because I'm like, this guy can change the fucking world if he could just learn to share his ideas with others. So that's what I mean by that. Back to the bell curve. Let's sketch our bell curve real quick. That's shitty, but it'll have to do. I'm going to put our little markers up here. And we'll put the calculations for them below. There's John. He kept trying to get into like grad school to like Yale and Harvard and shit like that, and he's smart enough to do it. But he never got in. He like applied a bunch of times. Never got in because he could not fucking write a good essay. His fucking communication skills were atrocious. One of the brightest minds I've ever met, though. All right, so in the center, the mean is 100. Each time we go to the right one, we have to add 1 deviation. So this would be 115. This would be 130. This would be 145. When we go the other way, we have to subtract. Minus 15, minus 1 deviation. This gets us 85, 70, and 55. So that's how the curve works. And this is how homework problems are going to ask you questions. It'll ask you shit like this. What percentage of the people or the population has an IQ between 85 and 130? Not percent, just 85 and 130. Question mark, that's what I want to put there. It's a question. So we come up here, I'm going to put my percentages up there real quick. That's 34%. This is 13.5%. This is 2.35 and 0.15. And we'll do the other way. 34%, 13.5%, 2.35, and over here 0.15. And they won't give you the graph. The question will actually come in the form, the IQ test has a mean of 100 and a standard deviation of 15. What percentage of the population has an IQ between 85 and 130? So the first thing you want to do is, draw the empirical rule. To then figure out the regions in question and add up those parentheses or percentages. Or find is a better region answer. Find the region discussed and add up the percentages. So 85 is right here and 130 is here. I have 34% plus 34% plus 13.5%. This is, I know the 34 and 34 is 68. 68 plus 13.5 is, I got a 0.5, I got a 1, I carry a 1. 81.5%. Does that make sense? So let me give you guys one. What percentage of the scores are greater than 115? So if I look at my chart up there, I have 13.5% plus 2.35% plus 0.15%. This adds up to 16%. And I think one of my favorite fucking stats comments ever. What percentage of the people you meet are below average intelligence? I love this line. I've seen people argue it. No, this isn't true. It's true. Well, average intelligence is in the middle. It's 100. And if we add up the scores left of it, you will find a rule that is true for every single bell curve graph whatsoever. Half the graph, if you do the dividing line at the mean, 50% is on one side, 50% is at the other side. So half the people you meet are below average intelligence. That includes everybody. At a college, if you're just talking about the people at a college, it's higher than that. While there are some people that go to college that are below average intelligence, it's not half. I don't know what the actual percentage is, but people that like, some people just don't go to college, like college is not for me. I never liked education. I'm not good with numbers or English and shit like that. The IQ score measures good with ability to work with numbers and letters. Generally, it's when you go to college, you have to develop those skills enough that you're above average. But not everybody is. You guys want to look at this? You're doing it in StackCrunch? The empirical rule is not in StackCrunch, but finding standard deviation is. I see people still running, so I need to slow my shit down. You have a question, or are you scratching your head? You were scratching your head. Never mind. All right. I'm going to use the data set I always use to represent shit, my stats project stuff. Height is a great category to do standard deviation off of because it follows a normal bell curve. So we're going to go stats, summary stats, columns. I'm going to tell it height. And that's the standard deviation we're looking for. In fact, I'll do mean, standard deviation, and variance. The mean height, or the mean height is, this is in inches. Something's off, because 52 inches is barely over 4 feet. This is a huge shout out that something's wrong here. The average height is not like 4 foot 3 inches. So we've got some errors in here. And I bet I can already see one of them right now. This person wrote that they are 5.9 inches tall. Right? I'm sure they meant 5'9". Right? That sounds right. So this is a lot like a bonus lesson. If something looks, don't just automatically accept what you see as the answer. This, in terms of height, every 12 inches is a foot. So this is 4 foot 4 inches. And that is saying the average height of people is 4 foot 4 inches. How many people do you know there that are like less than 5 feet tall? It's not a lot. There are people that are less than 5 feet tall, but not many. So for the average to be 4 foot 4, this is like a don't accept what you see. So what could we do to change this? What could we do to like address this? We could either go through and delete all those people, because I don't know for sure that they meant 5'9". Or I could take the time and calculate for them and replace it. I think I would probably go that route. I don't think anybody meant 5.9 inches. I would go through and say, this is probably 69. 5 feet is 60 inches and then 9 more inches. And I could go through and find all the one. Oh, look, there's a 5'4", a 5'2", 5'6", there's a 5. There's a bunch in here. So I could go through and edit them. But the real thing was we were looking to see where we find this. This is stats, summary stats columns. And you can see that if you take it out of a calculator and square 26.543, you're going to get it pretty close to 704.5. Because it's the variance square. Variance is standard deviation squared. Any questions? So on your homework, as you will see, we have homework for 3.2. We do not have homework for 3.3. I'm going to do 2 separate videos because if you don't care, you can leave, but wait till you hear the topic of 3.3.